Isaac Newton mathematically justified and formulated the most important law of universal gravitation of celestial bodies. Every two particles of matter always attract each other with a certain force. The principle of mass equivalence became the main foundation for Albert Einstein's general theory of relativity. The famous theorem allows treating large spherical planets as simple geometric material points.
Today, we're going to dive into one of the most profound laws in all of physics, Newton's law of universal gravitation. You see, for millennia, humanity looked at the heavens and the earth as two completely separate realms, each governed by its own set of rules. But with just one elegant mathematical formula, Isaac Newton unified them. He provided the quantitative key to a puzzle that had perplexed the greatest thinkers since antiquity. So here's our roadmap. We'll start with the historical context in An Ancient Cosmic Question. Then we'll get into the real heart of it with Newton's lunar proof. That's the calculation that proved his theory. After that, we'll formally state the law of gravitation, dig into the subtle but crucial idea of two kinds of mass, then look at the consequences of the law, and finally, we'll wrap up with a brilliant mathematical insight known as a spherically symmetric universe.
All right, let's begin with our first section, An Ancient Cosmic Question. We're going to trace how this idea evolved from just a philosophical musing into some really rigorous physics.
You know, the idea of some kind of force acting at a distance, that's an old one. Ancient scholars talked about parts of a whole just trying to reunite. And as you can see from this quote, Johannes Kepler had this remarkable intuition way back in the 17th century. He didn't see gravity as a one-way street. He called it a mutual affection, a kind of cosmic dance where the attraction was reciprocal. He and thinkers like Anaxagoras long before him, they sensed there was a force governing the cosmos, but they just didn't have the mathematical tools to prove it.
This timeline really puts into perspective the immense intellectual journey it took to get here. Think about it. Over 2,000 years before Newton, the Greek philosopher Anaxagoras correctly figured out that the moon's motion was the only thing keeping it from falling straight down to Earth. Much later, Kepler refined that idea, guessing it was a force that got weaker with distance. But it wasn't until 1687, with the publication of his masterpiece, the Principia Mathematica, that Newton finally nailed it down with a definitive mathematical law. It was really the culmination of centuries of inquiry.
And that brings us right to our second section, Newton's proof with the moon. This is the intellectual core of his discovery, this brilliant connection between the simple fall of an apple and the majestic orbit of the moon.
This was the revolutionary question Newton asked himself. And on the surface, they seem like totally different things, right? One is a local, everyday event, the other is a celestial ballet happening on an astronomical scale. Newton's genius was to just hypothesize that they were two sides of the same coin, the very same universal force, just acting over different distances. His job, then, was to prove it with math.
So, the starting point for his calculation was a number that was already well established. Thanks to the work of Galileo and others, it was known that any object in freefall, right here near the Earth's surface, accelerates downward at about 9.8 meters per second squared. This value, we call it g, was the terrestrial anchor for his whole celestial calculation.
Now here is the crucial piece of the puzzle, Newton's central hypothesis. He proposed that the force of gravity follows an inverse square law. To really get a feel for this, picture the force radiating out from the Earth's center in all directions, kind of like light from a bare light bulb. Now imagine this force passing through a series of nested, transparent spheres. The total strength of the force has to be the same as it passes through each sphere. But as the spheres get bigger, their surface area grows in proportion to the square of the radius. So for the total force to stay the same, its strength at any single point on the surface has to get weaker by that same factor, the square of the distance.
The next piece he needed was astronomical data. By his time, astronomers had figured out that the distance from the center of the Earth to the moon was about 60 times the radius of the Earth itself. This ratio, 60, was the key to testing his inverse square hypothesis.
Okay, so now we can put the hypothesis to the test. If gravity weakens with the square of the distance, and the moon is 60 times farther away, then the gravitational acceleration it feels should be our surface gravity, g, divided by 60 squared. So you take 9.8 meters per second squared, you divide it by 3,600, and you get a predicted acceleration of about 0.0027 meters per second squared. This is the number Newton's hypothesis predicted. Then, Newton did a completely separate calculation, this one based on the principles of circular motion. He calculated the centripetal acceleration needed to keep the moon in its orbit. That term just describes the constant inward pull an object needs to follow a curved path instead of flying off in a straight line. Using the Moon's known orbital period and its distance, he found that this required acceleration was, you guessed it, also approximately 0.0027 meters per second squared.
The numbers matched. The predicted acceleration from his inverse square law was identical to the required acceleration from orbital mechanics. This was the eureka moment. This was the unification. The force pulling an apple to the ground was definitively, undeniably, the same force holding the Moon in the sky, its strength just fading with distance exactly as he had predicted. The celestial and the terrestrial were one.
So, with this powerful empirical proof in hand, Newton could now lay out the principle in its full general form. And that brings us to Section 3, the law of gravitation.
And here it is, the law in all its glory. It states that every single particle of matter in the entire universe attracts every other particle. The size of this force, F, is directly proportional to the product of their masses, we'll call them m1 and m2, and, just as we proved, it's inversely proportional to the square of the distance between their centers, r.
The whole equation is held together by this term, g, the universal gravitational constant. This is one of the fundamental constants of nature, and its value is incredibly, incredibly small. And that tiny number explains why gravity, even though it runs the cosmos, is actually the weakest of the fundamental forces. You don't feel the gravitational pull of your desk or your chair because their masses are just too small for the force to be noticeable.
All right, now we're going to explore a more subtle but really profound aspect of Newton's work. Let's move to Section 4, two kinds of mass and the principle of equivalence.
So in Newtonian physics, the word mass actually does two different jobs. First, you have inertial mass, which comes from a second law, F equals ma. This is just a measure of an object's inertia, how much it resists being accelerated by any force. Then you have gravitational mass, the one in the law we're discussing. This determines how strong the gravitational force is that an object both exerts and feels. Logically speaking, there's no reason these two different concepts of mass have to be the same thing.
And yet, they are. They are absolutely identical. Every experiment we have ever conducted has shown that inertial mass and gravitational mass are equivalent to a mind-boggling degree of precision. This amazing experimental fact is what we call the principle of equivalence. Newton saw it and basically took it for granted, but it was this very principle that Albert Einstein later saw as a fundamental clue about how reality works. It led him to the incredible idea that gravity isn't a force at all, but is actually the curvature of space-time itself. And that, of course, became the cornerstone of his general theory of relativity.
Okay, so we've established the law and its nuances. Let's move on to Section 5, consequences of the law. We're going to explore how this one equation dictates the behavior of the universe. So a few direct consequences just pop right out of the math. First, mutual acceleration. Since the force is equal and opposite on both bodies, their accelerations have to be inversely proportional to their masses. The Earth accelerates an apple way more than the apple accelerates the Earth. Second, the relative acceleration between two objects is proportional to the sum of their masses, which is a key detail for precisely analyzing things like binary star systems. And finally, the law lets us define a gravitational potential, which basically creates a map of space where an object's potential energy depends only on its location.
This leads us to our final section, and it's a real testament to Newton's mathematical genius. Section 6, a spherically symmetric universe, and his elegant shell theorem.
Now, the law of gravitation, strictly speaking, applies to particles, but planets and stars, they're giant spheres made of countless particles. So how can we use the law? Well, Newton solved this by proving what we now call the shell theorem. Using calculus, which he had just invented, he showed that for any particle outside a spherical body, the net gravitational force from all the bits and pieces of that sphere adds up to be exactly the same as if the entire mass of the sphere were crushed down into a single point at its very center.
You really can't overstate how important this theorem is. It's a huge simplification. It lets us take these incredibly complex objects, planets, stars, and just treat them like simple point masses in our calculations. Honestly, without the shell theorem, celestial mechanics would be almost impossibly difficult. It's what makes the simple gravity formula so powerful and so useful.
So, in the end, Newton's law gave us this vision of a majestic, clockwork universe all running under a single, invisible, and perfectly predictable force. It reigned supreme for more than 200 years, but it told us how gravity works, not why. What is this invisible force, and what happens when you push this law to its breaking point, into regions of gravity so intense that mass stops just pulling on things and starts to literally bend the fabric of space and time itself? Well, that is where Newton's story ends and Einstein's begins.
Thank you, friends. Strive for understanding and become wiser. See you soon.